Dr. Bola, this is Bridget, and I'm going to be explaining the theory behind Lab 12, which is the concept of conservation and collision. So first off, a collision is where two objects come in contact with each other and impose a force upon one another. There are two different ways that we could analyze a collision. The first one is impulse, which is represented by the equation force times change in time, or there is change in momentum, represented by P, and I will further elaborate on that equation in a second. But the second part of the title is the concept of conservation. So basically we want to see, does momentum conserve itself if there are no external factors? We have predicted this from Newton's third law, which is that every action has its equal opposite reaction. So for a very simple demonstration, if I were to push against a wall, then the force that I inflict on the wall and the force that the wall imposes on me should be the same. Furthermore, if we have a collision, then the momentum before and then the momentum after should be the same. And the two components that make up momentum are mass times velocity. So the mass times velocity before and then the mass times the velocity by the end should be equal if there are no external factors. Okay. So now we're gonna go into the different types of collisions. Today we're just gonna go over two. We have the elastic collision and then the inelastic collision. I drew a couple of examples. So an elastic collision is where objects separate. So let's say you have a blue ball and a green ball coming towards each other and then they collide. And an elastic collision, they will separate and go their opposite ways. Whereas if you have an inelastic collision, then the objects will stick together. So the blue ball and the green ball are coming together, they stick, and then they go in the same direction. Okay, so this is now the part where I show you how we decided to test this in our lab. So we have these wonderful carts in the physics lab, and then there's a sticky side and there's a not sticky side. So when we wanted to measure the elastic collision, we would use the not sticky side so that they would bounce off of each other. But if we wanted to measure the inelastic collision, then we would use the sticky side so that they would go in the same direction and not part from each other. Okay, so let's discuss the first one so that I can better explain what's going on. So in the first one, we had an elastic collision where we had a stationary cart and then we had a moving cart. So we would shove the moving cart into the stationary cart. Then we used our Pascal interface and we would find the momentum right before the collision happens and then the momentum right after the collision happens. Then we would take those data points, put it into our Excel. Now to make sure that the law of conservation doesn't just work in one scenario, we would change it by adding more weight to one of the moving carts to see if the laws of conservation would apply to multiple scenarios. Okay, so now we've gone over the first one. The second one is very similar. We had a moving cart and then a stationary cart, but this time we put the sticky sides on. So this was an elastic collision. We wanted to see if the momentum would still equal one another. Then in 3 and 4, we had two moving carts going against each other. So in the first one, we had an elastic collision. The two moving carts collided. We gathered the data. Inelastic, again, flip the carts around, push them against one another, and then collect the data. And our theory is that if we were to graph the momentum before and if we graph the momentum after, we should get a slope of 1 because a number divided by the same number should equal 1, such as 3 divided by 3 should equal 1, 4 divided by 4 should equal 1. So yeah, let's see if it works.
First, we set up our track with two carts and placed a motion sensor on each end of the track. Both sensors were connected to the Pascal 850 interface, and we made sure everything was working and reading correctly in the software. We also created calculations in Pasco for momentum and kinetic energy for both carts, along with total momentum and total kinetic energy, so we could track what was happening during each collision. For our first activity, we focused on elastic collisions. We kept one cart stationary and pushed the other cart towards it using the magnet sides so they would bounce off of each other. We repeated this a few times while adding increasing amounts of mass to the moving cart. This let us see how changing the mass affected the momentum and energy during the collision. For the second activity, we kept the same setup but switched to the Velcro sides so the carts would stick together after the collision. This made it a completely inelastic collision. Again, one cart started at rest and we added different amounts of mass to the moving cart for each trial. This helped us compare how energy behaves differently in inelastic collisions compared to elastic ones. For the third activity, we went back to elastic collisions using the magnet sides, but this time both carts were moving toward each other before the collision. This allowed us to see how momentum is conserved when both objects are already in motion. In all three activities, we used the motion sensors to record the velocities of each cart before and after the collision. Then, we looked at the values right before and right after impact from the graphs to compare total momentum and kinetic energy and see if they followed conservation laws. After collecting our data, we exported it into Excel so we could better organize and analyze it. In Excel, we looked at the velocity values right before and right after each collision, then used those to calculate momentum and kinetic energy for both carts. We also compared the total momentum and total kinetic energy before and after each trial to see if they were conserved. Using Excel made it easier to clearly see the changes and confirm our results.
Do you want to make a cameo in our video?
So in this experiment, we tested the conservation of momentum principle across several different types of collisions. Those included both elastic and inelastic collisions, as well as trials with stationary and moving carts. So if you look at our data, we consistently saw that the total momentum before and after each collision was relatively the same. If you look at our elastic stationary trials, which I believe is activity 1, you can see that before collision we had values of 0.24 and then after collision 0.23. Super close. Throughout this trial we had a percent error of 7%. As we continued through the other trials, we maintained similar values. If you can look at our graphs on our Excel, and we had a slope nearly at 1 for every single activity that we did. Even when we changed masses or had both carts moving, the system still kept momentum nearly constant. The small discrepancies we saw are most likely due to experimental error with things such as drag of the cart on the track, slight measurement inaccuracies, or energy loss during the cart collision to things like heat or sound. Overall, our results strongly support the principle of the conservation of momentum, and regardless of the type of collision or setup, the total momentum of the system remained essentially the same, which confirms the theory that we already had going into lab, which made this pretty easy for us. Thank you guys.
A cool, real-life example of this is car crashes. Even though the cars get damaged and lose a lot of kinetic energy during the collision, momentum is still conserved. That's because some of the energy gets transferred into things like heat, sound, and the deformation of the cars instead of staying as motion. Because of this, investigators can actually use physics to estimate how fast the cars were going before the crash by analyzing how the vehicles move after impact. I think it's interesting because even in something as chaotic as a crash, the same conservation of momentum we test in this lab still holds true.